Imagine two particles separated by millions of kilometers. You manipulate one of them, and instantly, faster than the speed of light, the other reacts. Impossible. Einstein thought so. He called it spooky action at a distance and spent decades trying to prove the idea wrong. Welcome to the unsettling world of quantum entanglement, the phenomenon that challenges everything we think we know about reality, that has pitted the greatest geniuses of physics against each other, and that is now revolutionizing the technology of the future. Everything Newton had built, that predictable, mechanical universe where cause and effect worked like a Swiss watch, was beginning to crumble. In 1900, Max Planck discovered that energy is not continuous. It comes in packets, called quanta. Then came Einstein in 1905, explaining the photoelectric effect and showing that light also behaves like a particle. In the 1920s, things got really strange. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others created quantum mechanics. And what they discovered was disturbing. Particles can be in multiple places at the same time. You can't simultaneously know the position and velocity of a particle, and the simple act of observing changes reality. And the most bizarre thing of all, particles can be connected instantaneously, no matter the distance. This last point, quantum entanglement, went too far even for some of the theory's creators. And here begins one of the most epic debates in the history of science. On one side, Albert Einstein, the man who revolutionized our understanding of space, time, and gravity. On the other side, Niels Bohr, the father of modern quantum mechanics. For Einstein, there had to be something more, some hidden variable that would explain everything in a logical and predictable way. In 1927, at the Solvay conference, Einstein and Bohr engaged in intense philosophical debates. Einstein presented thought experiments attempting to prove contradictions in quantum mechanics, and Bohr patiently refuted each one of them. Einstein's most famous quote in that debate was, "God does not play dice with the universe." Bohr's response was equally iconic. Einstein stopped telling God what to do, but Einstein did not give up. In 1935, he prepared his final coup. Along with Boris Podolsky and Nathan Rosen, he published an article that would become known as the EPR paradox, after the initials of the three authors. It was a brilliant thought experiment, designed to show that quantum mechanics was absurd. The argument went something like this. Imagine two particles that interacted and then separated. According to quantum mechanics, they become entangled, connected in a mysterious way. If you measure a property of the first particle, say its spin, you will instantly know the spin of the second, no matter how far away it is. It could be on the other side of the universe. But here's the problem. According to Einstein's theory of relativity, nothing can travel faster than light. Nothing. So how does the second particle instantly know what happened to the first? Einstein had three options. Either quantum mechanics was wrong, or information traveling faster than light existed, violating relativity. Or particles already had their properties defined from the beginning. Einstein chose the third option. For him, it was obvious that the particles already knew their states from the beginning, and quantum mechanics simply couldn't fully describe that, making it clear that he thought the idea was too ridiculous to be real. Bohr and the so-called Copenhagen school disagreed. Reality was, in its essence, probabilistic and not local. But all of this was philosophy. No one could experimentally test who was right. For decades, the debate remained at an impasse. Einstein died in 1955, still convinced that he was right. Bohr died in 1962, championing quantum strangeness. It seemed we would never know the truth. Then, in 1964, an Irish physicist named John Bell entered the scene. It was possible to create an experimental test to decide, once and for all, who was right, Einstein or Bohr. Bell developed a mathematical equation, now known as Bell's inequality. The test was brilliant in its simplicity. If the universe functioned as Einstein believed, with hidden variables and local realism, the results of certain experiments would have to obey this inequality. If, however, quantum mechanics and its spooky action were correct, the inequality would be violated. The wait ended in the 1970s and early 1980s. Several physicists attempted to perform the test, but it was a Frenchman, Alain Aspect, who achieved the most conclusive results. In a series of brilliant and meticulous experiments, Aspect and his team used entangled photons and measured their properties. The result, each time, Bell's inequality was violated. Nature, at its most fundamental level, did not obey Einstein's rules. The spooky action at a distance was real. The universe is, in fact, as strange as quantum mechanics predicted. Aspect's confirmation was a physics earthquake. Entangled particles do communicate instantly, no matter the distance. But how is that possible? Doesn't that violate relativity, which states that nothing can travel faster than light? Quantum entanglement prevents you from sending a message. You can't, for example, manipulate your particle here on Earth so that your friend on Mars instantly receives a hello. Because, although the particles are correlated, the result of each individual measurement is completely random, and to make a comparison, you need to send this information through a traditional channel, such as radio or the internet, which is limited by the speed of light. So, Although the connection is instantaneous, it cannot be used for faster-than-light communication. Causality, the principle that the cause precedes the effect, is preserved. Einstein's relativity and quantum mechanics, strange as it may seem, coexist peacefully. But if we can't use it to send messages, what is quantum entanglement good for? This is where the story gets even more interesting. Classical computers, like the one you're using right now, work with bits, which are either 0 or 1. Quantum computers use qubits. Thanks to superposition, a qubit can be 0, 1, or both at the same time. And thanks to entanglement, you can connect these qubits in a way that a classical computer could never achieve. By entangling multiple qubits, you create a computational system with exponential processing power. A quantum computer with just a few hundred entangled qubits could, in theory, perform calculations that would take today's largest supercomputers billions of years to solve. This has enormous implications for areas such as new drug development, materials science, artificial intelligence, and, of course, cryptography. Internet security today depends on mathematical problems that are too difficult for classical computers to solve. But for a quantum computer, these problems would be trivial. That's why scientists are also using entanglement to create quantum cryptography. The idea is to use entangled particles to generate security keys. The beauty of this is that, if a spy tries to intercept the key, the very act of observing the particles would disrupt the entanglement. Both sides would know instantly that communication had been compromised. It is a physically inviolable security system, guaranteed by the very laws of quantum mechanics. In 2022, the pioneering work of Alan Aspect, along with John Clauser and Anton Zeilinger, was finally recognized with the Nobel Prize in Physics. The award celebrated how they transformed a philosophical debate into experimental science and paved the way for the second quantum revolution we are experiencing today. Quantum entanglement shows us that reality is far stranger, more connected, and more mysterious than our everyday intuition allows us to see. The spooky action that so troubled Einstein is, in fact, one of the most fundamental properties of our universe. And we're only beginning to scratch the surface of what we can do with it. The debate seemed destined to remain in the realm of philosophy forever. The first tests came in the 1970s with John Clauser and Stuart Friedman in Berkeley. They used entangled photons, particles of light. The experiment worked like this. They created pairs of entangled photons, sent each photon to a different detector, separated by several meters. They measured the polarization of each photon at random angles and compared the results statistically. And the results, Bell's inequalities, were violated. Quantum mechanics was right, Einstein was wrong, but the scientific community is skeptical by nature. There were loopholes in the experiment that could explain the results without actual entanglement. The three main loopholes were, the locality loophole, where the detectors were too close together. Perhaps there was communication between them. In the detection loophole, not all photons were detected. Perhaps those that were detected were not representative. And in the freedom of choice loophole, the measurement settings were not truly random. In 1982, Alan Aspect in France conducted more sophisticated experiments, separating the detectors by 12 meters and changing the measurement settings while the photons were in flight. Result: once again, Bell's inequalities were violated. In the 1990s and 2000s, increasingly elaborate experiments were conducted. Anton Zeilinger in Vienna. Entangled photons separated by 144 kilometers across the Danube River. There were experiments with particles separated by islands. In the Canary Islands and tests, using light from distant stars to ensure true randomness. Each experiment closed more gaps. Each result confirmed. Quantum entanglement is real. In 2015, 3 independent groups in the Netherlands, Vienna, and the United States conducted experiments that closed all major loopholes simultaneously. The experiment at Delft University, led by Ronald Hansen, was particularly elegant. They entangled electrons in diamonds, separated by 1.3 kilometers. The measurements were taken so quickly that, even traveling at the speed of light, no signal could have passed from one detector to another. And in 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger, precisely for these experiments with entangled photons and for demonstrating the violation of Bell's inequalities. The Nobel Committee was clear. Quantum entanglement is real. Non-locality is real. Einstein was wrong. Okay, so quantum entanglement is real. Particles can be connected instantaneously across any distance. But how? This is where things get really strange, because the honest answer is, we don't know completely. What we know is this: when two particles interact in certain ways, they become a single system, even if they are later separated. They are no longer two independent particles. They are a single quantum system, described by a single wave function. Imagine quantum twins, but not just any twins, twins who literally share the same existence. If one has spin up, the other instantly has spin down. Not because one sent a message to the other, but because they are, in a way, the same thing. It's like cutting a coin in half. You put one half in a box and send it to Mars. The other half stays on Earth. When you open the box on Earth and see the face, you instantly know that on Mars is the crown. But here's the crucial difference. In quantum mechanics, the coin was not defined as heads or tails until you opened the box. It was in a superposition, simultaneously, heads and tails, until the moment of measurement. And when you measure one, the other instantly collapses into its complementary state, no matter the distance. Does this violate Einstein's relativity? Technically, no. Because you can't use entanglement to send information faster than light, the measurement results are random. You cannot control whether you will get spin up or down. You can only see the correlation after comparing the results through normal means of communication. It's as if the universe has created a loophole in its own rules. It allows instant connections, but in a way that doesn't allow instant communication. Niels Bohr used to say, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. And he was absolutely right. But the story doesn't end here. Because in recent years, scientists have discovered how to see this bizarre phenomenon, and the applications are straight out of science fiction. Let's start with the most famous one, quantum computing. Your current computer, whether a smartphone or a supercomputer, works with bits. Each bit can be 0 or 1, on or off. It's binary, it's simple, it's predictable. A quantum computer works with qubits, quantum bits, and this is where the magic happens. A qubit can be at 0, at 1, or, and here's the tricky part, in a superposition of both simultaneously. It's 0 and 1 at the same time, until you measure it. But it gets better. When you entangle multiple qubits, they become a single system. 2 entangled qubits can represent 4 states simultaneously. 3 qubits, 8 states. 10 qubits, 1,024 states. With just 300 perfectly entangled qubits, you would have more simultaneous states than there are atoms in the observable universe. This means that a quantum computer can process an absurd amount of information in parallel. Problems that would take even the best supercomputers billions of years to solve can be done in minutes. In 2019, Google announced quantum supremacy, its Sycamore quantum chip, which solved in 200 seconds a problem that would take 10,000 years on the best classical supercomputer. In 2023, IBM launched Condor, with 1,121 qubits. China has built photonic quantum computers that process data 100 trillion times faster than the world's fastest supercomputers. But what is this used for in practice? Discovery of new drugs, simulating complex molecules to create new medicines, artificial intelligence, training AI models exponentially faster, optimization, solving problems of logistics, traffic, and resource distribution, finance, modeling markets and risks with unprecedented precision, and cryptography. And here we arrive at our next topic. All the security of the modern internet depends on a mathematical trick. It's easy to multiply to giant prime numbers, but extremely difficult to do the reverse. Take the result and find out what the original numbers were. This is called RSA encryption, and it protects your banking data, your messages, and your government's secrets. A classical computer would take millions of years to crack a modern RSA key. A sufficiently powerful quantum computer could do this in hours. This is both terrifying and fascinating. Governments around the world are panicking, preparing for coup day, the day when quantum computers could break all current encryption. But here's the twist. The same quantum entanglement that threatens current security could create absolutely unbreakable security. It's the quantum key distribution, or QKD. Here's how it works. Alice wants to send a secret message to Bob. She creates entangled pairs of photons. It sends one photon from each pair to Bob, and keeps the other. When Alice and Bob measure their photons, they obtain correlated results that they can use as an encryption key. But here's the brilliant part. If someone, let's call her Evie the spy, tries to intercept the photons and measure them, she inevitably disturbs the quantum state. Alice and Bob immediately detect the interference. It's physically impossible to spy without being detected. The laws of quantum mechanics guarantee this. It's not security based on complicated mathematics. It's security based on the fundamental laws of the universe, and it's already in use. China has built a 2,000-kilometer quantum communication network connecting Beijing and Shanghai. In 2016, they launched the Mishi satellite, which distributes quantum keys from space. Banks in Europe already use QKD to protect transactions. The Pentagon is building its own quantum internet. The race for the quantum internet has already begun, and entanglement is at its heart. Okay, now let's talk about the most mind-blowing application, quantum teleportation. Calm down. Before you get too excited. No, you're not going to teleport to work tomorrow. We're not talking about transporting matter, but we're talking about transporting quantum information instantaneously across any distance. And that's equally incredible. Quantum teleportation works like this. Alice has a particle in an unknown quantum state that she wants to send to Bob, but there's a problem. If she measures the particle to find out its state, she destroys the quantum information. The solution, entanglement. Alice and Bob share a pair of entangled particles. Alice makes a special measurement involving her original particle and her half of the entangled pair. This measurement destroys the original state, but transfers the information to Bob's particle. Alice sends the measurement result to Bob using conventional methods. Bob uses this information to transform his particle back into Alice's original state. The quantum state was teleported from Alice to Bob. The original particle was destroyed, but an exact copy was created on the other side. It's like a quantum fax that destroys the original. This was first demonstrated in 1997 by Anton Zeilinger and his team. Since then, the records have kept falling. In 2012, teleportation occurred across 143 kilometers in the Canary Islands. In 2017, China teleported quantum states from Earth to the orbiting Misha satellite, 1,400 kilometers away. Em 2019, teletransporte de qubit tridimensional, qubit, pela primeira vez. In 2022, teleportation via a quantum network with multiple nodes. And what is that for? Primarily to build the quantum internet, a global network where quantum information can be transmitted securely and instantly. Quantum computers in different parts of the world could work together as if they were a single system. Using entangled particles, quantum sensors have enabled scientists to create sensors thousands of times more precise than conventional ones. They can detect minuscule magnetic fields, measure time with absurd precision, or even map underground structures without digging. In medical imaging, entanglement can create imaging techniques that require significantly less radiation, crucial for safer medical examinations. Atomic clocks, the most accurate atomic clocks in the world, use entangled atoms. They are so precise that they wouldn't lose a second in billions of years, essential for GPS and telecommunications. In astronomy, telescopes using entangled photons can overcome classical resolution limits, allowing us to see details that were previously impossible to see, and we're only scratching the surface. New uses for entanglement are constantly being discovered. But all of this raises profound questions. What does quantum entanglement really tell us about the nature of reality? Quantum entanglement is not just a powerful technological tool. It forces us to confront some of the deepest questions about the nature of reality. If particles can be connected instantaneously across cosmic distances, what does that mean for our notion of locality? Does this refer to the idea that things can only influence their immediate neighbors? Classical physics taught us that the universe is local. What happens here only affects what is nearby, and this influence propagates at most at the speed of light. But quantum entanglement tells us that the universe is fundamentally not local. There is an intrinsic connection that transcends space and time as we know them. He used it as an argument against quantum mechanics, but experiments have proven that this phantasmagoria is an intrinsic feature of our universe. So, what is this ghostly action? Is it a secret message? An invisible bridge? The most widely accepted interpretation, the Copenhagen interpretation, championed by Niels Bohr, tells us that the properties of particles do not exist until they are measured. Before measurement, they are in a superposition of all possible states. The measurement forces the particle to choose a state, and in the case of entanglement, measuring one particle instantly forces the other to assume its complementary state. It's as if reality were a book that only gains its words when you read it. And if two pages are tangled, when you read one, the other also instantly becomes written, no matter where it is. This is profoundly counterintuitive. This means that reality is not something objective and pre-existing, waiting to be discovered. In a sense, reality is created or defined by the act of observation, but the Copenhagen interpretation is not the only one. The strangeness of quantum mechanics has led to other attempts to understand it. One of the most famous is the many worlds interpretation, proposed by Hugh Everett III in 1957. In this view, every time a quantum measurement is made, the universe splits into multiple parallel universes. In one universe, the particle has spin up. In another, it has spin down. All possibilities are realized. But in separate realities, in the context of entanglement, when you measure an entangled particle, the universe splits apart. In one universe, you see spin up and the other particle has spin down. In another universe, you see spin down and the other has spin up. All correlations are maintained, but without spooky interaction between universes. It's a fascinating idea, but it raises its own questions. How many universes exist? Another approach is Bohm's theory, or Bohmian mechanics, proposed by David Bohm. She attempts to reintroduce determinism and the hidden variables that Einstein so desired. In this theory, particles have well-defined positions and velocities at all times, but are guided by a pilot wave or quantum potential that extends throughout the universe. Bohm's theory is mathematically consistent and reproduces the results of quantum mechanics, but it is less popular because it is more complex and postulates this invisible pilot wave. The truth is that, despite all experiments confirming entanglement, the interpretation of what it truly means for the nature of reality is still an active field of debate among physicists and philosophers. What is undeniable is that the universe is far stranger and more interconnected than we ever imagined. The legacy of quantum entanglement is immense. It forced us to reevaluate the fundamentals of physics, gave us a new understanding of reality, and opened the doors to technologies that seemed like pure science fiction. The race to build more powerful quantum computers, global quantum networks, and ultra-precise quantum sensors is only just beginning. We are at the dawn of a new technological era, driven by that spooky action at a distance that Einstein so despised. What will come next? Simulations of black holes and the early universe, using quantum computers to unravel the greatest mysteries of cosmology. Quantum artificial intelligence, a new generation of AIs with unprecedented learning and reasoning capabilities. New forms of energy, perhaps even nuclear fusion, could be optimized with quantum assistance, and personalized medicine, with drugs and treatments designed for the quantum level of each individual. The journey of quantum physics, from Einstein's skepticism to the experimental confirmation of Bell, Baspect, Clauser, and Zeiling, it is a testament to the power of human curiosity and scientific persistence. She reminds us that even the strangest and most counterintuitive ideas, when based on evidence, can reveal profound truths about the universe. So, the next time you look at the night sky, remember, the particles that make up you, the stars, and distant galaxies may all be interconnected by an invisible web of quantum entanglement. The universe is not just a place of separate and isolated objects. It's a complex dance of instant connections, where reality is more fluid and interdependent than we could ever have imagined. He is not a ghost, he is the very essence of a universe that we still have much to learn. If you enjoyed unraveling this mystery with us, don't forget to like, share, and subscribe to the channel for more journeys into the heart of science.